In this video, we're going to be solving trigonometric equations. I recommend watching my video on the unit circle before jumping into this one. I've split this video up into levels, so I've got level 1, level 2, level 3, sort of to differentiate the difficulty of the equations. I've tried to cover a range of different problems, so to sort of give you a good idea of the different types of equations you'll need to solve for A-level mathematics. Okay, let's jump in then to level 1. We're really going to be starting with the basics of how to solve a trigonometric equation. Firstly, let's define what is a trigonometric equation. So a trigonometric equation is any equation where the unknown is part of the trig function. So for example, looking at this equation, sine x equals root 3 on 2, the unknown is inside the sine function. So we need some understanding of trigonometry in order to solve for x here. Okay, let's jump into this first example then. So the question says solve the equation sine theta equals root 3 on 2 in the interval 0 to 360 degrees. When they say solve the equation, they're really asking to find the value of theta, or the values of theta in this interval. Okay, let's start with our unit circle. I'm going to be using the unit circle mostly in most of these problems, although I will show you an example using the graphs as well and how to solve equations with graphs. Okay, so remember how we're defining the sine function? Firstly, picture a point on this circle, and you can think of cosine theta and sine theta as the coordinates of this point. Okay, so it has x and y coordinates of cosine theta, sine theta. Again, go back to that video on the unit circle if you're not sure about this. So now what this equation is telling you, if sine theta equals root 3 on 2, that's saying the y coordinate of this point is root 3 on 2. We also know there's another point on this circle in the second quadrant that will have this same y coordinate. So we can already see we're actually going to get at least two answers here. Okay, let's draw our radii in. And the question is, when this question says find theta, it's asking what is the angle of rotation starting from 1, 0 to this point on the circle. How many degrees have I rotated around the circle to get here, where the y coordinate is root 3 on 2? And actually, to find all of the solutions, all we ever need to solve trigonometric equations is this initial angle. Because using that initial angle, you can find the rest of the solutions. For example, because I know the angle in here is going to be the same as this angle I've labeled theta 1, then this angle of rotation to the second point on the circle is going to be 180 take theta sub 1. Okay, so this initial angle I call the reference angle, sometimes also called the base angle or principal value. I don't know why it has different names. It doesn't really matter what you call it. It's just the idea that we're finding this first angle to the first point, and that's going to allow you to find the rest of the solutions. Okay, so this reference angle is the inverse sine of the y coordinate. Now you may know the exact value of root 3 on 2. I've got a video on how you can remember exact values for trig functions, so check that out if you want. But if you take the inverse sine of root 3 on 2, then you get the reference angle of 60 degrees. What that's telling you is this initial angle to this first point here, the angle of rotation is 60 degrees. Okay, so that's actually one solution for our equation here. One solution is theta equal to 60 degrees. And now that we have that first angle, we can work out the second solution, the angle of rotation to the second point on the circle. 180 take 60, that's 120 degrees. And now make sure you check your intervals. So the next solution would be if we go all the way around the circle and get back to this point. So it would be 360 plus 60. Do I need to include that solution? No, because it's outside of our interval. So the only solutions for theta I get here are 60 degrees and 120 degrees. And that's our final answer. Okay, so this is the basic idea that I'm going to be using to solve the rest of the equations. As long as you understand the unit circle, it all sort of follows from that. But let's go through an example using the graphs, just so maybe you prefer using the graphs to solve equations. Okay, so this question says solve for theta in the interval 0 to 360 again. And we have the equation cosine theta equals negative cosine of 40 degrees. So to solve equations with the graphs, firstly you start, in this case we're going to start with the graph of the cosine function, because we've got cosine theta equal to something. And you could get a decimal for this negative cosine 40. If you plug that into a calculator, you get approximately negative 0.766. The next thing you do is to draw a horizontal line at this value. So we're going to draw a horizontal line at negative 0.766, and this is the line with equation y equals negative cosine 40. So let's interpret what this equation says in terms of the graph. This is saying the graph of the cosine of theta is equal to negative cosine 40, or is equal to this horizontal line. In other words, the solutions to this equation will be where this line intersects the graph of cosine theta. So what we're looking for is these points of intersection, where that horizontal line cuts the graph. To find the first point here, we take the inverse cosine of negative cosine 40. That gives us our first solution. If you put that into your calculator, you get 140 degrees. So this first point is at an angle of 140 degrees. And to find the rest of the solutions, you use symmetry, because the graph is symmetrical. If this angle is 40 degrees less than 180, this point must be 40 degrees more than 180. So yeah, basically just using symmetry. So this point here is at 180 plus 40, that's 220 degrees. And then again, check your interval. Are there any more points of intersection between 0 and 360? We can easily see there are not. So these are all of the solutions we need for this equation. So we get theta equals to 140 degrees and 220 degrees, and we're done. So that's using graphing to solve trigonometric equations. I prefer using the unit circle, so I'm going to proceed using the unit circle, but hopefully you found that useful if you want to use graphing instead. Okay, let's look at another level 1 example. This one says solve the equation sine theta plus cosine theta equals 0 in the interval 0 to 360. Okay, how to proceed here? Well, the main thing you're aiming for in trigonometric equations is to have one function on the left and some constant on the right. So for example, I want sine theta equal to 2 or tan theta equal to 1. I want some trigonometric function on the left of the equation and a number on the right. At the moment, I don't see any way to find the value of theta when the equation is written like this. So what I can do is to rearrange so that sine theta equals negative cosine theta. And can you see the next step? If I divide by cosine theta, I get sine theta over cosine theta equal to negative 1. So I'd have that negative 1 left over on the right if I divide it by cosine theta. But just be careful when you're doing this, because the trigonometric functions can equal 0. Remember, you cannot divide by 0. In this particular case, I can divide by cosine theta because we can see by inspection that it cannot equal 0. Because cosine of 90 is 0, but sine of 90 is 1, we can see that 90 would not be a solution to this equation. So there's no way that cosine theta can equal 0 and sine theta equal to 0. So I can divide by cosine theta, but just be careful when taking steps like this. When dividing by trigonometric functions, sometimes there can be 0. Be careful of that. Okay, so sine theta on cosine theta equals negative 1, therefore tan theta equals negative 1. This is where, now that I have my trig function on the left, my number on the right, I draw up my unit circle. So we were thinking of sine and cosine as the x and y coordinates of the point on the circle. How do we think about tan? We can interpret tan theta as the gradient of the radius. And because tan theta is a negative, we interpret this as a negative gradient. So do you remember what the negative gradient looks like? So one way to remember that is if you're a man walking across the screen, are you going downhill? Are you getting more negative, or are you going uphill? Are you going up? Is it positive? So downhill going across the screen is a negative gradient. So when the radius has a negative gradient, it's in the second quadrant and the fourth quadrant. Okay, if the radius is in the first or the third quadrants, it has a positive gradient. So that's how we know where the solutions will be. It'll be in the second or the fourth quadrants. And the first thing we need to figure out is this angle in here, the reference angle, the angle between the x-axis and the radius. To do that, we want, the angle when tan of theta equals -1. So we take the inverse tan of 1. Ignore the signs when you're finding the reference angle. Again, I hate to keep bringing it up, but go back to my video on the unit circle. I talk about how you can imagine a right triangle in here, and the sign of this number doesn't matter when you're trying to figure out that angle in there. So anyway, it's inverse tan of 1. Remember your exact values is going to be 45 degrees. So this angle in here is 45. But remember, the angle of rotation we care about is anti-clockwise, starting at 1, 0. So we actually want this angle. That's going to be 180 take 45. That's 135 degrees. Also, we want this angle going around to the second radius that we've drawn in. That's going to be 360 take 45. That's 315 degrees. And check your interval. Is that all of the solutions between 0 and 360? Yes, it is. So we get theta equal to 135 degrees and 315 degrees. Let's move on to some level 2 equations. These are going to involve, you can see we've got some squared terms. We're going to be factorizing. We've got some, we're going to have a quadratic equation here, and we're going to use one of our identities, the Pythagorean identity, which says that sine squared theta plus cosine squared theta equals 1. Okay, so let's start with this problem. It says solve the equation 4 sine squared x take 3 cosine squared x equals 2 in the interval 0 to 360 degrees. Okay, remember we want one function on the left and a number on the right. At the moment I have sine and cosine and they're both squared. The first question you can ask yourself is, how can I have this equation all in terms of one trig function? So how can I have it in terms of either sine or cosine? Well, we can use that Pythagorean identity. So use the identity cosine squared x equals 1 take sine squared x. You could also use sine squared x equals 1 take cosine. I think it would still work. I'm just going to choose to use this one. So I'm going to plug in 1 take sine squared x for cosine squared, and then I'll have it all in terms of sine squared x. Okay, so I've plugged that in for cosine squared x, then expand these brackets, so we get 4 sine squared x take 3 plus 3 sine squared x equals 2. Then 4 sine squared x plus 3 sine squared x is 7 squared x, and I can also add that -3 to the right hand side, so I get 7 squared x equals 5, then divide by 7. Sine squared x equals 5 on 7, then take the square root of both sides and I get sine x equals plus or minus the square root of 5 on 7. Okay, now we have that trig function on the left, the constant on the right. This is where we go to our unit circle. And remember how we're interpreting this. Imagine the point on the circle. That point there is going to have a y coordinate of positive root 5 on root 7. Then we have another point as well with that same y coordinate. We also need to consider here the negative value. So we're going to have points in the third and fourth quadrants as well with that same y coordinate, sorry, the negative value of root 5 on 7. Then draw in your radii. And we're trying to figure out that angle of rotation to that first point. That's going to allow us to find the rest of the solutions. So what is that? Well, we take the inverse sine of root 5 on 7. So that's the reference angle. Inverse sine of root 5 on 7. Plug that into your calculator. You get approximately 57.69 degrees. So that initial angle is 57.69. Then we can find the rest. So the second angle is going to be 180. Take that first angle, plug that into your calculator, you get about 122.3 degrees. Then the third point, the angle of rotation there is 180 plus that initial angle. 180 plus 57.69, rounded off, is 237.7. And the final point, the angle of rotation to that point, is going to be 360. Take that first angle we worked out. 360 take 57.69 is approximately 302.3 degrees. And then again, check your interval. Okay, so our final solution here then is x approximately equal to 57.69, 122.3, 237.7, and 302.3. On to the next one. This question says, solve the equation 2 sine squared theta equals 3, take 3 cosine theta in the interval negative 180 to 180. Okay, here we're going to be talking about negative angles as well. Okay, remember we want to have it all in terms of one function. How can we do that here? Well, we don't have a cosine squared this time, so we can't substitute in 1 take sine squared. What can we do? We can substitute something in for sine squared. So we're going to use the identity sine squared x equals 1 take cosine squared x. So we're going to substitute in 1 take cosine squared theta for sine squared theta. Alright, so we get 2 multiplied by 1 take cosine squared theta equal to 3 take 3 cosine squared theta. 3 take 3 cosine theta, sorry. Expand those brackets out, we get 2 take 2 cosine squared theta equal to 3 take 3 cosine theta. And here, let's rearrange this so we have all of the terms on the left and 0 on the right. So we could add that 2 cosine squared to the right hand side, subtract 2, do a bit of working out. You should end up with 2 cosine squared theta take 3 cosine theta plus 1 equals 0. Now what do we do? Well, this is actually a quadratic, right? We have something squared, then the middle term is just cosine theta, then we have that constant on the end. This is a quadratic, and hopefully we can factorize it. If you find it easy, you can write it as 2x squared take 3x plus 1 equals 0. So instead of writing cosine squared theta, just write x squared. And look at this equation. Can you factorize this? Are there factors of 1 and 2 that make negative 3? Well, if we make them both negative, then we can have that positive 1 and negative 3 in the middle term as well. So we get 2 cosine theta take 1 multiplied by cosine theta take 1 equal to 0. Double check, expand it out, make sure you get this equation. So once we've factorized, we can say that cosine theta equals a half or cosine theta equals positive 1. Okay, so this is just a general process of solving quadratics or factoring quadratics. You should know this from GCSEs. Okay, now that we have these two possible equations, let's go to our unit circle and let's think of the point on the unit circle. When we have cosine theta equal to half, that's saying the x coordinate of this point is a half. And we'll also have another point in the fourth quadrant with that same x coordinate. Okay, so that's how I would interpret this equation here. There's a point on the unit circle with an x coordinate of a half. So draw your radii in, and we're looking for that angle. Then let's think about what it means for cosine theta equal 1. When is the x coordinate equal to 1 on this unit circle? We'll already have that point actually marked in. It's over here at 1, 0. The x coordinate for this point, where the circle intersects the x-axis, has an x coordinate of 1, which is at 0 degrees of rotation. So that would be the point where cosine theta equals 1. So what will our reference angles be? We're going to need a reference angle for both of these equations. For cosine theta equal to half, this is an exact value. Hopefully you remember, when is cosine theta equal to a half? That's when the angle is 60 degrees. So cosine of 60 is a half. So we get reference angles of 60 degrees and 0 degrees. So this initial angle in here is 60. The angle of rotation of this point obviously is 0 degrees. And now is a good time to check our interval. So we have an interval from negative 180 to 180. That means we need to go in the negative direction. That's actually clockwise from 1, 0, going around this way. So this angle in here is going to be negative 60 degrees to this point. Okay, so what are all of our solutions in this interval? So we have 60 degrees, negative 60 degrees, 0 degrees. Are there any other possible solutions? So for example, I could go all of the way around to this second point in the positive direction, but we can see that's more than 180 degrees. So we don't need to include that solution. And actually, we can see after a bit of thinking that there won't be any more solutions for this equation. So our final answer here is theta equal to -60, 0, or 60. And remember, you can always double check your solutions by plugging them into the original equation. So for example, if you want to check 0 degrees, plug it in for theta in this equation, make sure that both sides are equal. Okay, on to the next one. This question says, solve the equation 2 sine of 2 theta take 20 equals 1 in the interval 0 to 360. Here we no longer have just a single unknown inside that function. Now we've got an expression inside the function. So let's have a look at how this changes things. First, we want to divide by 2, so we get sine of 2 theta take 20 equal to a half. Now we have that trig function equal to some number, some constant. Let's go to our unit circle. So how we're interpreting this equation, we're imagining a point on the unit circle with a y-coordinate of a half. Okay, and draw your radii in, and we're looking for this initial angle. So, well, sine of theta equal to half has an exact value. When is sine theta equal to a half? That's when the angle is 30 degrees. So our reference angle here is 30 degrees. That's that initial angle in there. And the angle of rotation to the second point is going to be 180 take 30. That'll be 150 degrees. Okay, so is this all of our solutions to this equation? There's not going to be any more solutions from 0 to 360. So surely we're done, right? So let's just write down what we've got so far. Remember, we've got an expression in here, not just one unknown. We've got 2 theta take 20. So we're going to get 2 theta take 20 equal to 30 degrees and 150 degrees. In order to solve for theta here, what we want to do is to add 20 to both of these answers. So we get 2 theta equal to 50 degrees and 170 degrees. And then divide by 2, so theta equals 25 and 85. Is this all of our solutions? Well, let's just have a look at another possible solution. So if we go all of the way around the circle back to this first point, that angle of rotation is going to be 390 degrees. How do we know whether to include this in our initial set of solutions for 2 theta take 20? Well, what you can do is to look at the interval, not for theta, but for 2 theta take 20. So firstly, consider the interval for 2 theta. If the interval for theta is 0 to 360, the interval for 2 theta will be these bounds multiplied by 2. So the interval for 2 theta is 0 to 720, that's double 360. Then the interval for 2 theta take 20, to find that we need to subtract 20 from each of these bounds. So 2 theta take 20 will be between -20 and 720 take 20 is 700. Okay, so for all of the solutions, we actually initially need to look at all of the angles between -20 and 700. So we do need to include this 390 degrees, and we also need to include the angle of rotation to the second point going around the circle twice. So to this second point, it would be 540. That's the angle of rotation if we go around and then 180 degrees again. So 540 take 30 is 510. So we need to include these two solutions as well. Then add 20 to both of those. That's 410 and 530 degrees. And then divide by 2. That's 205 and 265. And you can see they're within our original interval for theta. Okay, and that is our final answer for theta. 25, 85, 205 and 265. On to some level 3 equations now. We're really going to step up the difficulty here. I hope it's not too much for one video. Again, the aim was to sort of go through a range of problems that you will encounter in A-level mathematics. So to solve these, we're also going to be using the other types of identities from A-level mathematics, the sum and difference formulas. For example, sine of A plus B is sine of A cosine of B plus sine of B cosine of A, and the double angle formulas. For example, sine of 2 theta is 2 sine theta cosine theta. For all of the formulas and an explanation of those, check out my videos on trigonometric identities if you're not sure about either of these two. Okay, so let's jump into the first one. It says solve the equation 3 cosine theta equals 2 sine theta plus 60 in the interval 0 to 360. Remember, the goal here is to get one function on the left and some number on the right. At the moment we have cosine and sine, And it would be nice if this was just sine theta, we could divide by cosine theta and have tan theta, but unfortunately we can't because we have sine of theta plus 60. So we have to deal with this first. The way we deal with sine of theta plus 60 is to use our sum and difference formulas and expand out this function here. Okay, so firstly, using the sum formula for sine, we're going to have 3 cosine theta equal to 2 sine theta cosine 60 plus sine 60 cosine theta. These are in your formula booklet for A-level mathematics, so it's not something you need to remember, which is nice. So now that we have used that formula, we can expand out these brackets, so we need to multiply both by 2. And also we can use the exact values for cosine 60 and sine 60. So let's plug those in as well. So we're going to have 3 cosine theta equal to 2 multiplied by a half, that's cosine 60. Sine theta plus 2 multiplied by root 3 on 2, that's sine 60 cosine theta. 2 times a half is just 1. 2 times root 3 on 2 is just root 3. So then we get 3 cosine theta. Also I've subtracted this from the left hand side, so we get 3 cosine theta take root 3 cosine theta equal to sine theta. And then we can factorize the cosine theta and divide by cosine theta. I'm going to take a few steps in one go here. So I get tan theta equal to 3 take root 3. Again, I'm using the fact that cosine theta cannot equal 0 in this case. So we get tan theta equal to 3 take root 3. Now we have that trig function on the left, the numbers on the right, so we go to our unit circle now. Remember how we're interpreting tan? That's the gradient of the radius. This is a positive number, so a gradient of the radius is going to be positive. It's positive in the first and the third quadrants. So we have our radii in the first and third quadrants. Then we're looking for this initial angle to that first radius. To find that initial angle, we take the inverse tan of 3 take root 3. That's our reference angle. Plug that into a calculator, you get approximately 51.7. So that angle in there is, we can round off to 51.74. That's one of our solutions. And then in this interval, we're going to have another solution, the angle of rotation to the second radius. That's going to be 180 plus 51.74, which is about 231.7. So we get solutions for theta of approximately 51.74 and 231.7. Just a note here that often is the case that you want to give your answers to the same number of significant figures. So here I've used 4 significant figures for both answers. Sometimes it'll be, 2 decimal places or 1 decimal place, but sometimes it will be, say, 3 or 4 significant figures. So anyways, they're your final solutions for that question. The next one says solve the equation 3 cosine 2 theta equals 2 cosine squared theta in the interval 0 to 360. Here we have a double angle. So we're going to be using our double angle formulas, but which one should we use? Remember, cosine 2 theta has 3 possibilities. There's cosine squared take sine squared, or 2 cosine squared take 1, or 1 take 2 sine squared, if you remember those 3. So which one should I use? Well, we want all of this in terms of one trig function, so I'm not going to use 1 take 2 sine squared or cosine squared take sine squared. The one I'm going to use is 2 cosine squared take 1. So plugging that in then for cosine 2 theta, then it will all be in terms of cosine squared. Expand out the brackets. 3 times 2 cosine squared is 6 cosine squared. 3 times negative 1 is negative 3. So we get 6 cosine squared take 3 equal to 2 cosine squared theta. Then subtract 2 cosine squared from the left hand side. 6 take 2 is 4, so we get 4 cosine squared take 3 equal to 0. And then rearrange in terms of cosine theta. So add 3, divide by 4, we'll get cosine theta equals plus or minus root 3 on 2. This is the point where we draw up our unit circle. Drawing a point, now we have positive and negative solutions for cosine, so we're going to have points in the first and fourth quadrants. That's going to have a value of positive root 3 on 2. Then we also have points in the second and the third quadrants. That's going to have an x-coordinate of negative root 3 on 2. Draw in your radii, and then all we need is this initial angle here. To find that, take the inverse cosine of root 3 on 2. That's one of the exact values, hopefully you remember. So the reference angle here is going to be 30 degrees. That initial angle is 30 degrees. Using that, we can find the rest of the solutions. So this second solution is going to be 180 take 30, 150 degrees. Third point, angle of rotation is 180 plus 30, 210 degrees. And the fourth point, 360 take 30, that's 330 degrees. And then check your interval. Is that all of the solutions in our interval? Because the unknown, the subject of the function is just theta. It's not an expression. It's not 2 theta or whatever. We don't have to mess with this interval. We can see that's all of the solutions. So we get theta equal to 30, 150, 210, and 330. The final question, this is really a step up in difficulty. I wanted to stick a harder problem in here. I hope it's not too different from the rest, but let's get into this one. So it says solve the equation 6 cosine theta take 8 cosine cube theta plus 1 equals 0 in the interval 0 to 360. Okay, what to do here? Well, it's tricky to say how to begin. I guess my focus will be on what to do about this cosine cubed. Well, one thing I can try first is I can see that I can factorize a cosine here. So that's something I might try initially. So the first thing I would try for this equation is actually factorize the negative 2 and then divide by negative 2. So I've subtracted that 1 from the right hand side. Divide by negative 2, we get 4 cosine cubed take 3 cosine theta equal to a half. Then I'm going to factorize the cosine theta. I could have done it in the previous step as well. But let's try that. So we get factorizing cosine theta out of those two terms. We get cosine theta multiplied by 4 cosine squared theta take 3 equal to a half. Now, what can I try? Well, this expression here, 4 cosine squared theta take 3, kind of reminds me of one of the identities for cosine 2 theta, one of the double angle identities. So the next thing I might try is see if I can somehow rearrange this so I get 2 cosine squared theta take 1. Is it possible to get that from this expression? Well, yeah, right? If I split this 4 cosine squared into 2 plus 2 cosine squared theta, then maybe I can get this double angle identity for cosine theta. Okay, so let's try that. We've got cosine theta equal to 2 cosine squared theta take 1 plus 2 cosine squared theta take 2. So here I've split the 4 cosine squared into 2 cosine squared and 2 cosine squared, and I've also split the negative 3 into negative 1 and negative 2. So now I can substitute in cosine 2 theta for 2 cosine squared theta take 1. But what am I going to do about this 2 cosine squared theta take 2? Okay, so I'm going to substitute in 1 take sine squared for cosine squared. So my next line is cosine theta equal to cosine 2 theta. That's substituted for all of this. And then cosine squared, I've substituted 1 take sine squared for cosine squared. So 2 times that, take 2 equals a half. Expand these brackets. This will be 2 take 2. So all we're going to end up with here is negative 2 sine squared theta. So my next line is cosine theta multiplied by cosine 2 theta take 2 sine squared theta equal to a half. My next thought is this is kind of looking like one of my sum and difference formulas. Okay, so let's expand these brackets and see where we can go from there. So multiplying by cosine theta, we get cosine 2 theta. And here I'm going to write sine squared as sine theta. So cosine 2 theta take 2 sine theta cosine theta. That's, after expanding the brackets. 2 sine theta cosine theta sine theta. What's this in here? 2 sine theta cosine theta, that's the identity for sine 2 theta. So let's sub in sine 2 theta for this. Cosine theta cosine 2 theta, take sine 2 theta sine theta equal to a half. Now what do we have here? Does this remind you of anything? Hopefully thinking of cosine of a plus b. Remember, cosine of a plus b is cosine of a cosine of b take sine of a sine of b. So we can write this expression as cosine of 2 theta plus theta equal to a half. In other words, cosine of 3 theta equal to a half. Okay, so after all of that, we have that trig function on the left, the constant on the right, and we can finally solve this for theta. Yeah, that's a bit of a step up from the previous problems. Hope not too difficult. Okay, so cosine of theta equal to a half. Let's proceed with our unit circle. Picture that point, because it's positive, it will be in the first and the fourth quadrants, and the x-coordinate is a half. Okay, so we have that x-coordinate, drawing your radii, and we want to figure out that angle. Again, remember your exact values. When cosine of theta equals to a half, that angle is 60 degrees. So this angle in here is 60. So that's one of our solutions for 3 theta. 3 theta equals 60 degrees. Now is a good time to think about the interval. What will be the interval for 3 theta? Well, let's multiply the bounds by 3. The interval for 3 theta will be from 0 to 540. That's 180 times 3. So we need to include all of the solutions from 0 to 540 for 3 theta. So that's going to be this one. That's 360, take 60, that's 300 degrees. And if we go around to this first point again, that's going to be 360 plus 60, that's 420. And if I go around a second time to the second point, that's going to be greater than 540, so I don't need to include that solution. So all of my solutions then will be 3 theta equal to 60, 300, and 420. If I divide by 3, I get theta equal to 20, 100, and 140. And that is my final answer for this question. Again, it's always worth going back to the original equation, trying these angles to make sure, when you plug them in, you get 0. Okay, so that is it for this video. By no means did I cover all of the things you need to know for trigonometric equations. There's just, it's such a large topic. There's so many things you need to, practice, I guess. And the thing I would say is just try lots of different problems for yourself. I will be doing more videos on this topic, covering, harder equations, different equations, little tips and tricks you can use to solve these types of questions. And as always, thanks for watching. Please leave a like if you appreciated this video, subscribe if you want to see more content, and I'll see you in the next one. Bye for now.